We've got another equation up here on the board. This is a little bit different from the last one in that in the last one we did have the option of solving for y. We got two different formulas for y. Here, I don't really see solving for y as an option because I don't know how to isolate y when I've got it as two copies of y. It's also the input to tangent and it's the input to the exponential function. So we're going to have to rely on implicit differentiation if we want to find dy by dx. Remember the concept behind this. I don't actually know what this graph looks like, but I know any equation in x and y describes some curve. Now, it probably doesn't look like that, but that would be a pretty gnarly curve. But the basic idea there is if I wanted to find the slope of the tangent line at that point, which is what dy by dx represents, I can basically just say, well, okay, this fails the vertical line test, but that doesn't. That passes the vertical line test. Just that part of the curve is a function, where y is a function of x, and the formula for that function, even though I don't have it explicitly, it's encoded in this equation. So I'm going to go ahead and say that although I don't have an explicit formula for it, I'm just going to view y as being a function of x. I find it helpful to put y in parentheses. That reminds me that it's a little bit different from x. I'm thinking of that as a function of x. And here, for example, it's the inside part of this function composition being plugged into tangent. So I'm saying this left-hand side is some function of x that I've built out of x's and y's. This is some function of x. They're the same, so I can take the derivative with respect to x of both sides. All right, here, this is a function composition with y as the inside part. The derivative of e to the something is e to the something times the derivative of that inside part. I'm going to choose to write that as y prime just because it takes less time to write than dy by dx. You're welcome to write it either way. Here, this is a product. X is being multiplied by tangent of y, and tangent of y is, of course, a function composition. So here I'm going to be using product rule. So we'll have the derivative of x times tangent of y plus x times the derivative of tangent of y. And that's going to equal. Now here I'm taking the derivative of 2 times y. Here I have y in parentheses, but it's not really the inside part of a composition because I'm not plugging it into some other function. I'm just taking 2 copies of it. Okay. And I didn't have a formula for y, but I had a name for it. So similarly, I'm not going to have a formula for its derivative, but I'm going to have a name for it. So if I have 2 copies of y, that's going to give me 2 copies of y prime. I get a y prime when I take the derivative. I can view that as do exactly what I'd do if this were x. If this were 2x, I'd take the derivative and I'd get 2, and then multiply by the derivative of y, which is the y prime. So I can still sort of think of it as chain rule with y being the inside part, but I really just think of it as, hey, 2 copies of y, that's going to contribute 2 copies of y prime. One word of warning here. A lot of times I see people write 2y times y prime. For some reason, just having a multiple of y, people want to make the derivative more complicated. It's not. If you have y and you take the derivative, you get y prime. That's it. All right, and then minus the derivative of x squared. That one is a function of x, so that's going to be minus 2x. All right, before we move on, I want to just point out, actually, before we move on, I want to finish taking the derivatives. I've got some d by dx's to do. All right, so e to the y prime plus derivative of x is just 1 times tangent of y plus x times the derivative of tangent would be secant squared, and that's still evaluated at y, times the derivative of the inside part, which is y prime. And that equals 2y prime minus 2x. Now, before we solve for y prime, I want to make a couple of notes. First of all, if I count in the original function, there were 1, 2, 3 y's. If I stop at this point, when I'm done taking the derivatives, before I do any algebra to get y prime by itself, I've got 1, 2, 3 y primes. That should always match. Okay. Every y that I have in the original is going to contribute exactly 1 y prime when I take the derivative. If it was a function composition, there's a y prime that comes from multiplying by the derivative of the inside part. If it was just some y's, that's going to contribute just some y primes. The other thing I want to point out is that the y primes are never plugged into another function. I'm not going to see e to the y prime, though I might see e to the y. I'm not going to see tangent of y prime. I can see tangent of y. That's because the chain rule never has me plug the derivative of the inside part into something else. It just has me multiply by the derivative of the inside part. And that's going to ensure that it's possible for us to solve for y prime, which is what we need to do now. So I've underlined the y primes. Looks like I have 2 of them on the left and just 1 on the right. So I think I'm going to move this term over to the left, and then I'll move this term over to the right. I'm just going to separate so that every term on the left will have a y prime in it. None of the terms on the right will. So this piece stays put, so it'll be e to the y, y prime. I'm going to move this piece in a minute. This piece stays put, so plus x secant squared y times y prime. And I'm going to move this piece over, so it becomes minus 2y prime. That's going to equal. The negative 2x can stay on the right, and remember we said we needed to subtract over that tangent of y. So now every term with a y prime in it is on the left. Every term on the right does not have a y prime in it. What that means is I can factor out the y prime. So we've got y prime times the quantity e to the y plus x secant squared y minus 2 is equal to negative 2x minus tangent of y. And that's going to mean that y prime will equal what I get when I divide by this quantity. Now, as a general rule, not crazy about dividing by quantities with variables in case they're 0. But this is the last step in this problem, and it's going to be understood, of course, that if what shows up on the denominator is 0, the formula is not valid. At that point, either the derivative doesn't exist just because it doesn't exist, or perhaps I have a vertical tangent. Okay. But in any event, the derivative would not exist. So we get negative 2x minus tan y over e to the y plus x secant squared y minus 2.